Launched by NASA in 2018, the Parker Solar Probe embarked on an unprecedented mission to touch the Sun, venturing closer than any spacecraft before it. Its primary goal is to unravel two of the Sun's greatest mysteries: why its outer atmosphere, the corona, is millions of degrees hotter than its surface, and how the solar wind is accelerated to incredible speeds. The Sun's structure includes the visible surface, the photosphere, and its expansive outer atmosphere, the corona. The corona is a superheated plasma, a state of matter where atoms are stripped of their electrons. This temperature paradox, known as the coronal heating problem, puzzles scientists. How can the corona reach millions of degrees Fahrenheit when the photosphere is only about 10,000 degrees? The probe's journey involves a highly elliptical orbit, utilizing Venus for gravity assists to gradually draw closer to our star. As of December 2024, it made its closest approach, coming within 6.1 million kilometers of the Sun's surface, a truly remarkable feat of engineering. During this daring maneuver, the probe achieved an astonishing speed of 690,000 kilometers per hour, making it the fastest human-made object in history. The spacecraft is equipped with a robust solar shield, essential for protecting its sensitive instruments from the Sun's extreme heat and radiation. Its key instruments, fields and sweep, are designed to investigate electromagnetic fields and measure the solar wind plasma environment. One of Parker's most significant achievements was penetrating the Alfvén surface, a critical boundary where the solar wind's speed surpasses the Alfvén speed. This boundary is crucial for understanding how the solar wind, a continuous stream of charged particles, is accelerated away from the Sun. The probe also observed magnetic switchbacks, rapid reversals in the magnetic field within the solar wind. These switchbacks are disturbances within the solar wind, now understood to originate near the solar surface. Theories attempting to explain the coronal heating problem include nanoflares, Alfvén waves, and magnetic reconnection. These mechanisms are thought to inject energy into the corona, heating it to extreme temperatures. Parker's solar probe's discoveries are vital for comprehending stellar physics and protecting Earth from the impacts of space weather. The mission has also uncovered a cosmic dust-free zone close to the Sun, a region where solar radiation pressure has pushed dust particles away. This provides new insights into the dynamics of dust in our solar system. The Parker Solar Probe continues its mission, expected to make observations until 2026, pushing the boundaries of our understanding of the Sun. Its journey is a testament to human ingenuity and our relentless quest to explore the cosmos. Beyond its tremendous speed, perhaps one of the most interesting questions to ask about the Parker probe is how this vehicle withstands the extreme temperatures we've been talking about. After all, in the region where it is now, we're talking about temperatures on the order of 1.5 million degrees Celsius. At such a high temperature, wouldn't this spacecraft just melt completely? The answer actually lies in a very simple physics distinction between temperature and heat. Simply put, temperature expresses how fast the particles in a system are moving, while heat corresponds to the total amount of energy those particles transfer. The solar corona is a region where there are comparatively few particles to transfer energy. Therefore, although the particles in the corona move at very high speeds, that is, although they have high temperature, they cannot transfer the same amount of energy, that is, heat, to the spacecraft. You can compare this to the difference between sticking your hand into boiling water and sticking your hand into a hot oven. When you put your hand in an oven, the particles inside the oven have high kinetic energy, high temperature, but they can't transfer heat the way a medium dense with particles like boiling water can. The logic behind Parker not melting away near the Sun is very similar. Of course, temperatures in the millions of degrees are still far too high for any spacecraft. To handle this, Parker carries a state-of-the-art heat shield. This heat shield consists of two carbon composite plates, and the sun-facing side of the plates is coated with a special white ceramic layer applied with plasma spray. In this way, the spacecraft reflects a very large fraction of the heat coming from the Sun. The approach is so effective that while the sun-facing plate reaches about 1,000 degrees Celsius, The scientific instruments in its protection, in its shadow, remain at about 30 degrees Celsius, a completely safe level. In addition, the spacecraft's solar arrays circulate about 3 liters of water in a continuous loop. As the water flows through the panels, it absorbs heat and then radiates that heat into space, thereby keeping Parker's own thermal balance. Of course, although the data Parker has obtained so far and the images it has sent back to Earth are extremely important for understanding the Sun's corona, we can even say the mission is only just beginning. In the next 4 years, Parker will make 16 more close passes by the Sun and continue to provide Earth with data about the Sun. The Sun is the only star we have the chance to study from this close, and likely it will remain so throughout human history. That's why understanding the Sun is a very important opportunity to better understand the physics of all other stars in the universe, both Sun-like and not Sun-like. Scientists will try to make the most of this opportunity with Parker. See you in the next video. Goodbye.